Good morning, everyone. Today we'll be discussing or continuing with Seborg section 2.2, which is basically deriving our equations or initiating where to start, something like that. And then we are going to cover degrees of freedom. Degrees of freedom, I am going to, let's say, skimp over a bit, purely for the fact that we will be doing that in a little bit more detail during the course of the next couple of lectures when we do specific examples for kind of known systems. But it is extremely important, and yeah, in the next couple of weeks you'll get a lot more experience in that in any case. Okay, I can't exactly remember what I said and did not say about table 2.1 yesterday. I'm going to do a quick overview of the first couple of things that I think we discussed, so 1, 2, 3, and then we'll discuss the rest of those. But in any case, when we want to derive our model for our process or plant or whatever, first thing that we mentioned that is important is the objectives of that model. I think I did spend a lot of time on this, but we need to know what to understand what the objective is so that we can determine the model complexity. Without knowing the model complexity, we aren't sure what assumptions we can make. If we don't know what assumptions we can make, we obviously can't simplify that model. And if we make the incorrect assumptions, then obviously we are removing some of the important parts of that model. Not making any assumptions, we're obviously overcomplicating the system, and therefore it is extremely important to know that what the objective of that model is. So you have to have an idea of what you want to do before you can start determining the model of the system. You can't just go and say, hey, let's write all the equations in the world down and see which are applicable at the later stage. That's a very time-consuming way of doing it. Second, which I would assume is probably not necessarily, consecutive to one. It can be done prior, but the schematic diagram, it's one of these. I'm a picture kind of guy, not picturesque, but picture kind of guy. So I like drawing diagrams. I like to see what I'm working with, and that's one thing that is really very important to me, something that you'll notice in the semester test and exams as well. I like asking questions to draw diagrams and to represent a worded problem in the form of a diagram or schematic. And this, like I said, aids us in understanding the system as well as verifying that we are actually including all the variables or inlets and outlet streams that we are supposed to. And just take note that inlet and outlet streams that I'm referring to is not necessarily pipelines. These streams, I'll put them in quotation marks, can refer to energy streams, so energy losses and inputs in other forms like a electric heating element or something like that, which is not necessarily an actual stream. I did think about this issue yesterday afternoon, late night sometime. I didn't mention yesterday when I spoke about the actuators and so forth. An actuator, that word refers to something, in my mind, it refers to something mechanical, something that you can look, see or feel. That is not necessarily the case in the control system. That's why I prefer using the word final control element, which is a lot more ambiguous, let's say. But in the event of an electrical heater, there's no physical moving thing that is your final control element. In that case, a solid state relay, which is an electronic device, no moving parts except for some flip-flop stuff in a microprocessor kind of way or integrated circuit. That is basically your final control element, which executes the commands of the controller, basically just switching the element on and off at a rapid rate. but more on that later on, perhaps only in CPB. But if you are interested, let me know. I know a bit about these things, so if you're not sure what I'm talking about, just send me a message and I will gladly assist. All right, so third step, list all assumptions. Important what I say below that. Don't make an as of you, of me and you, or you and me, or whichever that saying goes. Assumptions are extremely important. Assumptions are your worst nightmare as well. So be careful. You know, you need to understand what you want to do. You need to understand what you need to do in order to make the correct assumptions. Then I think that's where we stopped yesterday, if I'm not mistaken. Point number 4, a lot of words. Spatial variation, that's the important one. So spatial variation of your variables would refer to, best example that I can come up with in the what we wrote on the screen here. What's the difference between a CSTR and PFR? And someone tell me, is there spatial variation in a CSTR? If we refer to the concentration, let's say. Anyone in chat with quick fingers? No spatial variation in a CSTR, that's correct. There could, however, be energy variation or not. Are we going to assume that that is also perfectly mixed? Typically, if we say CSTR, we will say that it's also perfectly mixed in terms of energy variation, so that we assume that the temperature is roughly constant. Otherwise, it gets extremely difficult. But most definitely in a plug flow reactor, we will have spatial variation in concentration. So point number 4, basically the point that I'm trying to make as well, is if we have spatial variation, then obviously we have partial differential equations with respect to certain variables, whether the concentration or temperature varies in that system or in that unit vessel, unit process, in terms of the actual spatial orientation of it. So that is a very important thing just to consider, and that kind of comes from your assumptions. So if you don't make the assumption of CSTR, then obviously you must include some form of spatial variation in your equations, which complicates the model a lot. So when we are considering something that could be considered as a CSTR and you don't make that assumption, you've already crossed that boundary of too complex, and you should probably just revisit the first couple of points in this table. Right, then number 5, I took some time to brush up on all my languages, and that is not what I came up with, so I just typed in translate in Google, but conservation laws, mass and energy balances is everything that we work with. It is the most important thing in engineering, probably in the world, because they govern all the stuff that we are doing, except for gravity. That's Newton's stuff. But in any case, if you don't understand what I'm saying, there might be a language that you can hopefully relate to. And yeah, obviously that's important. That's basically the basis of our model, because that is where our differential equations most likely arise from. Some additional ones, obviously, but these ones are the basis or the fundamental part of chemical engineering. And that's why we start with that in first year in CIR, whatever the code is. So I'm not going to say more on that. Then point number 6, equilibrium and algebraic equations. Which one of the equations or relations that I wrote there is not appropriate to the system or to any, well, not appropriate to this point? Can anyone tell me? No one? Are all of them appropriate? Andre, that is unfortunately incorrect. The 2 times sum of xi equals 1 plus 1 does make a lot of sense. Marinique, you're correct. Saturated steam, that is the correct one. And no, I'm lying again. Saturated steam is extremely important, and I'm going to test you on this, and you're going to fail that test. If I mention saturated steam, that implies a temperature and pressure relation. It is vapor-liquid, not really vapor-liquid equilibrium, but it's a form of equilibrium expression. So be very careful when you see the word saturated of any stream, not necessarily just steam, but if it's a saturated thing, it specifies more than one variable. So be careful about that, because this is a point that a lot of people make a mistake when they are developing models and neglect to consider the fact that a saturated stream needs only one specified either temperature or pressure to fully define that stream. But yeah, that equation, sum of xi, that makes no sense. It's correct if x is something that actually ends up being 1, but yeah, couldn't think of a good expression for x. That's just there to confuse you. Right, so v equals ah, that sort of, these sort of equations are the ones that relate our mass and energy balances to more specific variables that we can isolate. So in the event that we're controlling level, we don't want to work with volume because it's not the direct variable. Level is the height of the thing. So height times area is obviously volume. We do have d rho v over dt, but that we want to get rid of all those constants that we can introduce to ensure that we work with the simplest form of the variable that we are associating it with. You can obviously just continue with v, and somewhere in all your equations, your simulation, write it such that you work with v, but we do want to kind of simplify it such that it's extremely easy to fault find and track our variables in our set of equations. Okay, then we do a degrees of freedom analysis. So I drew an arrow down for controlled variable, manipulated variables, and disturbance variables. The degrees of freedom doesn't determine those. We need to specify, but the degrees of freedom analysis eventually boils down to how we specify those. So we don't specify them yet. We first want to simplify a little bit, and then after that, we end up with our full set of equations, variables, and constants, and then we specify which we are going to control, which we are going to manipulate, and which we are going to assume as, well, not assume, but not really specify either, which we must take as disturbance variables. And the question I'm asking around point number 8, why do we want to simplify any further if we already made some assumptions? Isn't this already done? And the answer is not necessarily. We are making a number of assumptions at the beginning, something like it's a constant tank reactor, but let's say our system does include some form of energy balance as well. So initially we introduced an equation that relates the heat losses to the wind in Uganda. And it seemed like that was a valid equation at that point in time. Now we come to a point where we sit with a number of equations. We do some simulations of that or verify it against plant data or known data. And we realize, oh, that only has like a 0.001% effect on our actual set of controlled variables that we are looking at. Now we can say, well, let's just scratch that one because it's only complicating the set of equations, our model, and there's no real reason. We don't want to work in inaccuracies of 0.001%. We are engineers, we aren't chemists or physicists. So at that point in time, you just reevaluate some of the equations that you introduced, check their effect or the magnitude that they magnitude of change that they can introduce into the system, and then from that point on you perhaps scratch some of those. Sometimes we might realize that there's a equation that we perhaps neglected, and then obviously just go back and revisit that from the start. Right, I just want to check Alex's question. Alex, yes, that's correct. Yeah. So this point number 3, well, basically point number 3, yeah, let's say point number 3. It is not necessarily something that you can learn. That is something that comes with experience most of the time, but also something that needs to be tested for. Simply making a number of assumptions, because that's what the textbooks do in our undergrad studies, is not always the correct answer. It is so that is like a knife edge. Going toward the left, you fall off onto the side where it's oversimplified. Going to the right, you dump into the overcomplicated system. And it's extremely difficult just to say, look at the system on a piece of paper and decide, okay, it's going to be too much if we do this, or too little if we do that. It really boils down to understanding how these things work, and that's why as engineers you need to develop this, let's call it the sixth sense of understanding, what the magnitude or the order of magnitude of certain things are. So I think you guys probably also had that in CIR. We introduced concepts like, what's the volume of a bath? What's the wattage of a element in your geyser at home? How long does it take a kettle of 2 liters to boil? These sort of questions come with time and, being observant. And I must admit, I'm not dissing your age group or anything, but nowadays a lot of people don't have any clue on how these sort of things work, or any understanding of it. And I am going to have to exclude Alex in this conversation. But in any case, I would very much like to implore all of you to be more observant from normal day-to-day activities. Think about stuff. Don't just assume, someone invented it and it works perfectly. Critically think about things. Try and evaluate, measurements without using a tape measure. Figure out what is 2 meters by 2 meters. Look at your room or your garage or something like that and say, well, what is the size of this without measuring it? Train yourself to actually be able to determine these quantities. And it's not only measurements in terms of meters, energy, heat losses, things like that. Right off the bat, can anyone tell me what heat does a human being roughly radiate? Assuming he's a sphere and not a chicken. Any idea? 800 watt that's a bit high. It can go up to about 100 watt. So in kilojoule would not be, so when I talk about energy, it's usually energy transfer, so that would be, per time. And that's what we are working with. So careful of the actual kilojoule quantity, specifically in dynamics, because it's not time related. Right, enough about that. I think last point, classify our controlled variables, manipulated variables, and disturbance variables. So the first thing, controlled variables, that obviously comes from our first point. What's the objective of this model that we are developing? What do we want to control eventually? Not being able to answer that question from the start is you not being able to do your job properly. So always ensure that you understand and know what needs to be controlled for a specific system. So you kind of do one by almost doing 9 in this table. So don't hold the chronological, the sequential order of table 9 as firm and fixed. It is something that, they obviously need to word it somehow that you can read it in a textbook, but it is not something that necessarily happens perfect per that order. Okay, so we should know what the control variables are. The manipulated variables, we not always just specify because we want to. There are means and ways of analyzing which variables are best to control a specific controlled variable. We'll get into that in process control next semester, but it's not always the case that we have a CISO system, something that you should start to get used to as a single input, single output system. If you have a single input variable, obviously that variable must be the one that you try to manipulate for your single output, your controlled variable. But most of the time, not a lot of the time, probably most of the time, you get multiple input, multiple output systems. In such a scenario, one input variable has a chance of being more, let's say, more important toward another controlled variable than an other input variable. So it's not that we just go willy-nilly and specify these manipulated variables. There are ways that we analyze for this and ensure that we have the most important, the most relevant manipulated variable paired with a controlled variable. And that pairing is what we basically do in the control stage of this exercise, which you don't yet do in any case. And then finally, disturbance variables. These are obviously things that we can't just specify. We have to kind of know where they come from and what they are. So in the sense where you are in charge of a specific section of a plant, then your disturbance variables, most definitely, a lot of them will come from upstream processes and not necessarily only upstream processes. Let me quickly draw this. If we have let's say a boiling tank or something like that, where we introduce some energy and we supply a vapor to a downstream process. The pressure here is it can be disturbed by a downstream process. If a downstream process opens a valve or uses more of that substance, whatever it is, then that pressure is disturbed from a downstream process and not only an upstream process. So just note that disturbances aren't fixed to inputs. It can be something that comes from a downstream system, and the same goes for manipulated variables. It's not always inputs that you manipulate. Sometimes it can be an output that you manipulate to enable a form of control in your system. So be very wary of trying to think of it as, inputs are manipulated variables and inputs are disturbance variables. It's not necessarily the case, because these systems are connected in a lot of ways, or some of them at least. Right, can't remember if we touched this, but obviously I'm just going to quickly run through this. I hope you know this by now. Mass balance accumulation equals in minus out. Component balance, accumulation of a specific component is that component in minus the output plus whatever is generated or consumed in there. Always make sure that you keep track of the signs of your generation term. So try to kind of memorize a specific way of writing that equation where generation is positive, same as in, and whenever you have some form of a consumption, then you need to ensure that the signs are correct. so that you have the correct way of representing it. Then our energy balance. Obviously, accumulation of energy inside the systems, whatever is coming in terms of the enthalpy and those sort of things, minus out whatever heat is added due to reaction or due to steam used to introduce more energy into the system. Heat added also refers to heat losses, but these losses is obviously in this term now a negative component. And then finally, plus the work done on the system. So we remember from thermodynamics that if you have a stir into a tank or whatever, that stir actually introduces energy in terms of work. Now, I'm asking the questions that the textbooks state we can neglect potential energy and kinetic energy. Those two we can assume as zero. Work we can assume as zero. Is that 100% correct? Can we do that all the time? Someone with an answer, please. That is the correct question. No, we cannot always assume that. If now, well, the last, let's say, about 25 years or so, there's been an introduction in microreactors, reactors with, microliters and smaller even volumes. If you have some form of work in something like that, then that form of work might be important in terms of energy balance. If you have a small hot plate stirrer with 1 or 2 or 3 milliliters of stuff in it, it might be important. Or if you have a massive rotary kiln or something like that, the actual work done by that might actually cause some effect. So be careful of just assuming it's zero. Do a back of an envelope calculation, check yourself, and then sure, if you are making this assumption that potential or kinetic energy is zero or work is zero, just check it quickly and go from there. Otherwise, you're going to say to your line manager at some point in time, now I assumed it was zero because the textbook said so, and he's going to say, well, you're a bad engineer because you're not making correct decisions or taking correct decisions based on your actual experience, but based on what you memorize from a textbook. That's not what we're supposed to do. We make good informed decisions based on guesstimates. Oh, and then I need to mention that the Q, which is this, obviously, that heat addition, that can be a tricky one every now and then to figure out, because that is where we need to ensure that we make the correct decisions on whether ambient temperature is a disturbance variable or not, whether some other temperature or effect or heat loss is important or not. Like I'm not sure what Ryan handles in CIO nowadays, but in terms of radiation, back in my time when I did heat transfer, it was often mentioned that we assume radiation is zero. That assumption can bite you in the ass like no other. So be careful and ensure that you know what assumptions you can make and when to make them. Right, the blending system. We are going to do this again, but not just yet. Yes, Alex, you do need to do that, not necessarily in form of an equation, but you need to compare it. When one day when you are old and experienced, you might be able to say, well, that system won't have radiation, but that at a lower temperature will have significant radiation due to X, Y, Z. And the reason why we are assuming radiation is zero in our undergrad, because it is almost use the swear word, extremely difficult. I've done advanced heat and mass transfer, Radiation, got significant experience using radiation terms. It is bloody difficult to get that correct. It's a very difficult thing to analyze for. Anywho, let's start with what we were supposed to do, I think, today, which is degrees of freedom. And this is extremely important. But I also mentioned that I'm going to kind of run through it rather quickly. It is not too difficult. It does get tricky, but we'll provide you with enough exercises and so forth just to hone your skills in this aspect. Okay, so degrees of freedom basically states that we need enough equations to satisfy the number of variables that we have so that we have a unique solution to our system. If we don't have that, we obviously get a system where either we are overspecified, which means you have a dependent equation or something like that in your system, or you forgot about a specific variable which should be introduced. Or if we have fewer equations, then it's underspecified. Then we have an infinite number of solutions for our system. Obviously, we can't work with an infinite number of solutions because that would be extremely difficult. We have to, how do we design for a volume of a tank if that tank height can be anything in the world? So it's not possible. We don't work with those things because we can't, specify it. And I want to just show you that if we have something like this, no, go away. If we have something like this, which we tend to want to write in matrix form, we eventually end up with a matrix from our coefficients that determine the effect of the variable toward our calculated, our output. But that can get extremely big. And remember when we said that determining dynamic models from fundamentals, from first principles, is extremely expensive. And that expense comes from human resources, so that the money going into a person having to sit there and doing these calculations and someone to check it, because you can't just have one person doing that. It's prone to have a lot of errors then. So think about it, if we think about a plant like Sasol or even SAPI or something like that, you might have thousands of variables and equations covering a specific system, and you don't want to do that by hand or in this sort of matrix form. Then you want to start simplifying with semi-empirical systems so that you rather just fit the model to a data set to control that. Okay, so I think you have seen this equation from CIR, either second semester one or the second year one, but number of degrees of freedom, or the degrees of freedom, NF, is equal to the number of variables that we have minus the number of equations. A very simple equation, but a very powerful equation. And we obviously have three scenarios. When NF is 0, we have a fully specified system, so we have one solution to that, and that is the only thing that we want to work with. We don't work with degrees of freedom greater than 0 or degrees of freedom smaller than 0. If it's greater than 0, obviously we have to specify something else because we have open degrees of freedom, which makes our system solvable by an infinite number of solutions. And then NF smaller than 0, you did something wrong, it's overspecified. You need to reduce some of your specifications that you introduced, or there might be some incorrect equation or variable specification. Okay, so the textbook provides us with a table of how to handle these degrees of freedom things. I don't really like the form of it, but in any case, you can make your own decision on that. Basically, first step, we decide all our constants. So in cases of a physical tank or something like that, remember the equation V equals AH. A obviously being a constant, rho depends on whether we make the assumption whether our density of incoming and outgoing streams is the same or constant or so forth. Then we can make that assumption. So then we list these constants. Once you're satisfied that all of those constants have been listed, then we can move on and determine the number of equations that we have. So we write all our equations, and we obviously specify all our variables. Now, this is where I like to use the diagrams, schematic of the system, so they can see what comes in, what goes out, so we can specify the correct variables. Doing so from head or just from a worded problem can be difficult, so hone your skills on that diagram drawing part and draw it neatly. Tests and exams, I always like to award some portion of the marks to the neatness of a diagram, not to penalize your artistic skills, but to ensure that you can convey the information accurately. I've got a little gripe about the way we treat communication in engineering. A lot of us say, well, I'm an engineer, so I can't spell or I can't, type a document or a report. That is so useless, because if you can't convey the information, then whatever you do is null and void. It is extremely important to properly and accurately communicate the information that you build up or that you research. Because if you can't do that properly, then you can't actually use that work that you did. So that's why I like to assign marks or award marks to being able to draw a proper diagram and doing it neatly, because if it's not done neatly, then there's a chance for errors or mistakes or inaccurate interpretation, and that's just poor communication and not what an engineer should be. Right, then obviously we omit t. T is obviously a variable, that's most definitely the case, but it's the independent variable. So t governs all the other stuff because that's the uber independent variable of dynamics. It's obviously time. So we do everything in respect of time, and that's why it is not included as a variable, because you can't really give an equation or a constant to t in this sort of setup. So yeah, just know that t is not one of your variables. It is an independent, totally excluded variable that governs everything else that we do in here. Okay, I wish I had a bottle of water next to me, but fortunately it's almost done. So after having a number of equations and a number of variables specified, we obviously determine our number of degrees of freedom by means of the equation, and then we know what variables are solved for, so we know what outputs we can get from that system. And then I don't like the separation of 4 and 5, but in any case, 5, what should we spec? That is where we come in and say we have now determined that the degrees of freedom is 2. So we need to specify 2 things. And that we do by introducing our manipulated variables and disturbance variables. So if we identify a disturbance variable, let's say we identify one disturbance variable, then we know, okay, that takes up 1 degree of freedom, we have 1 left. Because there's a disturbance we want to control, we need a manipulated variable, and that will take up the 2nd degree of freedom. And let's fortify this information by this extremely by this extremely important example that is ever present, and you'll see that even next semester because it's everywhere. Can anyone tell me? Let's start at the beginning. What should we do? What should we do first? first step in our deriving the equations and determining degrees of freedom. Quickly, we have 9 minutes. Exactly, what are we trying to achieve? Give me 2 variables that you think. Most definitely yes. These 2, those are our control objectives. We don't want to control what's coming in because it's impossible to control what's coming in. We just take it as it is. So our control objectives is obviously x plus w, or not plus, that's a bad, x and w. So the flow rate out and our concentration of whatever is blended in there. Let's list some of the assumptions. Anyone can give me an assumption. Very good. Those 2 are perfectly correct. I indicate that this stirrer is running really fast, so we are going to assume it's a CST, excluding the R, constantly stirred tank. Let's call it that. Oh, there is already a T. So that means that there is no spatial variation, correct? So we don't need any partial differential equations with respect to the concentration inside the tank. Second assumption, we assume constant density. That is a bit of a dodge one, depending on what x is. But in this case, we're going to have to do that because it's not necessarily the case, but usually it is so density is weakly paired with the concentration. So it shouldn't be a bad assumption. It shouldn't make too big a difference. We will probably still be in that 5% accuracy range that that at least I work in. Sometimes when I'm really lazy, we push that up to 20%. You may not do that. Right, so we listed some assumptions. Those seem all good. Now, give me some constants to this system. Rho obviously being one of them. Why is x2 a constant? Why is v a constant? Sandile, definitely. Tank is bold. Tigan, I hope I pronounced that correct. Temperature, yes, that is constant, but is it relevant to our system? And now I'm going to say yes, that's most definitely relevant because volume is obviously a function of temperature. Higher temperature, something expands. But if we refer to density as a function of temperature, which obviously implies the volume of the tank, that is so small compared to what the flows might be. And we are going to assume this tank is relatively big, let's say 2,000, 3,000 liters, maybe even 20,000. So temperature, without more information, you should actually include temperature as a variable and just check for that, because that's where we, let's say we have very little information. That's in that point 8 where we say simplify. We'll refer back to temperature and say, is that now really important or is it not? Atmospheric pressure, same goes for that in terms of temperature. Density is more dependent on temperature, not really more dependent, but the atmospheric pressure will change so insignificantly. In Pretoria, we have typically 86 kPa. That can go down to about 84 kPa. 90 is really high. And if you evaluate the change in that pressure, which will affect the volume of something, is basically insignificant. So we're not even going to list that as a constant. For now, yep, row and A. Equations. First thing we do, what's the first thing? Mass balance, most definitely. And that is going to look like what? Correct? Second thing, component balance, most definitely yes. Almost made a fool of myself. Let's say X1, row not B. Is that correct? Any other equations? Energy balance, what would that be? I'll leave that to you. Submit a assignment on the energy balance of this system by tomorrow 12 a.m., 12 p.m., noon. Let's make it 1, so 1300 hours. There will be no submission for that because there's no energy balance associated with this. If we refer to this system, you don't see any temperatures. When it's not shown in the diagram, you can assume that the inflow, regardless, the system is shown in this diagram as such. Temperature is not one of the factors. The moment we did something like that, yes, then energy balance, because now we are trying to do something else that needs to be heated or cooled. So we want to vary temperature with time as well. I think I'm going to stop there for today. We are at this point. I will upload these notes shortly after this lecture. Then please just continue on this one and see if you can get to the final point where you can determine what the degrees of freedom of this is, and we'll chat about that, I think, on a Slack discussion during the course of today, tomorrow, and maybe over the weekend. How does that sound? Next week, Monday, we'll continue with 2.4.1 and 2.4.2, perhaps 2.4.3 as well. I hope you have a good Friday and rest of Thursday, as well as enjoy your weekend. Enjoy it while it lasts, because it's going to be one of your last that you can actually kind of relax for a little bit. We're going to start the project soon, and then you will be busy all